Okay, so this is our redox lab or a redox titration. Don't forget that titrations represent a chemical procedure where we use a known amount of one chemical to answer how much of the other, whether it's gravimetric using a scale or volumetric using volumes, which can most of the time is acid-base, but here's an example of a titration that's a redox. Okay, so what are we going to do here? The whole purpose of the lab is take oxalic acid. It's an organic compound, and we want to figure out its concentration. Okay, and knowing the concentration of the titrant today is potassium permanganate. The analyte is oxalic acid. So as we've done volumetric titrations before, we've done acid-base, there are huge similarities. I made a 0.01 molar concentration. And what we're going to do is do a redox titration. Now, in this titration, we're going to take the permanganate ion, MnO4 negative, because the K plus is soluble, it's a group 1 ion, it spectates. And we're going to react it with oxalic acid, which is H2C2O4. Now, it's going to cause oxalic acid. By the way, it's kind of a cool compound. It's a double Ku group. So that's what it looks like. But we're going to force it to oxidize. It doesn't oxidize so easily, so we're going to force it to oxidize. I can do that.
You had it right the first time.
Yeah, you're right. I don't know what I'm doing. I wasn't sure. And we're going to make, of course, CO2. Okay, so we're going to force it to become in its carbon's most oxidized form, which is CO2. All right, so we'll make CO2s, and we're also going to make Mn plus, okay, 4 here, 2. Okay, now, if we look at the permanganate ion closely, and I'll rewrite it here, MnO4 negative 1, and we look at the oxidation state of the manganese, okay, we know the whole thing is negative 1, okay, and we know that each oxygen is negative 2. It's 2 away from becoming stable. Hey, there's 4 of them. 4 times negative 2. Hey, it's negative 8 overall. What must the charge of the manganate be if the whole thing is negative 1? Well, plus 7. So we've got a plus 7, okay, going to a plus 2. And so clearly, what's happening is in order for plus 7 manganese to become plus 2, it's got to rip not protons but electrons away. It's going to force the hand. If we're doing a titration, whether it's acid-base or redox, this is a driven reaction. And so what we do here to analyze the analyte, okay, we're going to force its hand by ripping electrons. Because it's a strong oxidizing agent, and we talked about this previously, a plus 7 surrounded by 4 oxygens, okay, it's going to really, with a very huge positive standard reduction potential, it has the great ability to force this to be spontaneous. Okay, now what we're going to do is we're going to figure out how much of this volume that I need, times it by its concentration to get moles, and try to take the moles of KMnO4 that are needed to react with this exact number of moles. It will not be 1-to-1 like acid-base. 1 hydroxide is 1 H+. We're going to have to balance that, okay? And since this is redox, we have to change our wordage a little bit. We're not going to neutralize here. We're not going to reach an equivalence point in terms of H+ and OH-. But we are going to reach an equivalence point in terms of electrons, okay? So oxalic acid is in here. How do I stop the titration if I'm not using acid-base indicators or a pH probe? How do I know that I've added just enough of the MnO4 negative that will completely oxidize all of the oxalic acid? Well, there's going to be a color change because the Mn plus 4 is a purple color. So we're going to use the color of the oxidation state. It's called crystal field theory here. The MnO4 is purple. And when it's completely reduced. It's an oxidizing agent, so when it gains its electrons to become +2, it goes colorless. So we're going to use that to our advantage. When I pour or drop or titrate KMnO4 into the analyte, the oxalic acid, okay, the MnO4, or the Mn specifically, is going to yank electrons from the oxalic acid. It's going to go clear, as if you had what? Phenolphthalein or acid-base indicator. How do I know it's ended? When this color persists for 30 seconds. Now, I don't know if I have purple in my hand because I'm colorblind, but what I do know is that I know that the reaction is over and I've reached the, quote, the end point of the titration when I've oxidized all of the oxalic acid, when a little bit of purple color persists. Why would the purple color persist? Because there's no more what? Oxalic acid to gain electrons from and change into a color solution. So when the purple persists, it means you've run out of all the electrons that the oxalic acid can give, which means that you have completely oxidized all of the oxalic acid. That's the difference here. Everything else is the same, okay? But we're not going to use a 1-to-1 ratio. Okay, so there's an issue here, as if we've done with acid-base volumetric titrations. If I use a strong base as a parallel to what we're doing here to drive a weak acid to completion, like we've done in many titrations, like the aspirin lab, okay, or the vinegar lab, okay? The problem with a strong base, just like a strong oxidizing agent, it reacts with other things. So even though I'm telling you I made a 0.01 molar solution, I can't be confident that is the concentration. So what must I do before I do this? Because it's so reactive, what do we do with the base? KHP. We standardize with KHP. So we're going to have to standardize this. So the first part of lab is standardization. So the purpose of the lab, okay, is to find the concentration of oxalic acid. I'm going to need to know exactly this concentration, just like in our aspirin and Tums lab. These titrations are based upon knowing the other chemicals' value. I made this, but it's going to be a little bit less. So here comes the first step. We must standardize. Now, I'm not going to standardize with KHP because KHP is a weak acid. It's a strong base. We're going to standardize with something else that will lose electrons. So this is the first part in your lab. It's a standardization, and we're going to balance together. Okay, so let's do this first part. Okay, so let me talk about the standardization. All right. So the standardization is to figure out the exact concentration of my permanganate ion before I can do this titration. All right, so in the standardization, I'm not going to use oxalic acid. I'm going to use a solution that has iron +2. And that concentration of iron +2 is known to be 0.10 molar. That's known. And I'm using 10 milliliters of it. And you can clearly see, party people, by knowing the volume of my analyte and its molarity, I get moles, okay? And from that moles, I can determine the molarity here, knowing the volume dropped. I'll show you how to do that. But before we can actually do this, we have to balance. So in your worksheet there, it's a standardization, and it has the following. It has MnO4 negative, okay, going to Mn +2. It also has Fe +2 going to Fe +3. Those are the two half reactions. We're going to put them together. So party people, I'm just going to deal with the first one. Okay? So let's go balance this. Okay? Using our more advanced balance method. The first step is to know that MnO4 negative will become Mn +2. That's for sure. That's something that'll be given to you. I'm going to balance everything other than oxygen and hydrogens. There's one Mn, there's one Mn. That's good. Now I have 4 oxygens. How do I balance the 4 oxygens in the more advanced method? I have to add how many waters? 4 water molecules, correct. Why 4 water molecules? Because I balance the O's with water, and there's 1 oxygen per that. Okay, by doing that though, now I have 8 hydrogens. I balance the hydrogens with H pluses. So this will be 8 H pluses. This is a skill you should have down. Then the last step is to balance the charge. If you look very carefully, this side is +2, this side is +7. Each side of a half reaction must balance the mass and the charge. I balance the charge with electrons. Each electron is -1. So how many electrons and where do they go in order for both sides to have the same charge? Anyone? You would need 5 electrons, because a -5 plus a +7 is a +2. And you have +2 on both sides. A half reaction has to have the same charge on both sides. So that is the correct half reaction. Look at this. The permanganate ion is going to grab 5 electrons. Hey, it does so because it is an oxidizing agent. It rips electrons away. Okay. What about the other chemical? The chemical that I'm using to standardize this with? Well, we're going to go with Fe+2 solution, and it becomes Fe+3. Notice its oxidation number is increasing. Why is it increasing? Because it's losing an electron. But I use the same rules to balance this. Balance everything other than oxygen and hydrogens. Hey, 1 Fe, 1 Fe. There is no oxygen and hydrogen, so I'm done. Now I balance the charge. +2 on this side, +3. Hey, I have to add an electron here so that both sides have the same charge. And that is the correct half reaction. However, to get the overall reaction, and that is what we need in our stoichiometry to solve this, we have to balance our electrons. Notice Fe+2 is giving up 1 electron, and notice that the permanganate rips 5. So we have to balance the same number of electrons that are lost to gain. So we multiply and find a common factor, which would be 5 between them. So to make this 5, so that the amount of electrons gained and lost are the same, I multiply and distribute the 5 all the way through. We've been through this. And now by balancing my electrons, I have automatically balanced the overall reaction. I'm going to write the overall reaction just as I'm asking you. Now, you should have recognized that we don't write the electrons because they cancel. And also, potentially we could cancel other things here if they were, but they don't. There's no H pluses on this side or water. So the overall reaction is 8 H pluses, okay, we're doing this in an acidic environment, plus 1 permanganate ion, plus 5 Fe+2 goes to 1 Mn+2 plus 5 Fe+3 plus 4 H2O. And why did we do that? Because we needed this ratio. There is 1 permanganate per 5 Fe+2. That's what we need. Okay, so how do we do the standardization? We're going to go do it in a second. But what do we do here? I'm going to fill up the burette with potassium permanganate. You're going to zero it out. I already have a beaker already measured out with 10 milliliters of Fe+2. It also has 10 milliliters of sulfuric acid. So therefore, there's what? There's H pluses in here. Remember, this is done in an acidic environment. And there's Fe+2. And so what you're going to do is you're going to add, carefully add the titrant, okay, to the analyte. And you're going to stop when the potassium permanganate persists, just like you were using an acid-base indicator, but you're not. When you're done and the slight purple color persists, you're going to measure the volume of your KMnO4. What's the whole purpose of standardization? To find the molarity. To find the molarity, you're going to use that volume. Make sure that volume is in liters. But now we need what? Moles of what? MnO4. How do we get that? Well, watch. knowing in the beaker I had 0.01 molar solution, and I had what? 10 milliliters. When I multiply liters times molarity, what do I get? Moles all the time. So this is going to give me 0.001 moles of Fe plus 2. I got to convert that to MnO4. How do I do that? Hey, get rid of Fe plus 2 and give me MnO4 negative. For my balanced chemical reaction, I know that there is what? 1 of these per 5 of these. And what's that going to give me? That's going to give the moles of my permanganate. I have the volume in liters, and that's going to solve for the actual concentration. I made carefully 0.01 of potassium permanganate. It's driving the reaction. It's reactive. It's going to react in the air. It's going to be a little bit less. So what we're going to do now is do this titration. And we're going to solve for, okay, the known or the actual concentration of the permanganate. Once I have that, I can use that for the second titration. Notice the color of the waste beaker. It's purple. Okay, what we're going to do is keep the waste beaker here. I'm going to fill up the burette with potassium permanganate. That's that purple compound. Okay, it's purple because the manganate, the Mn, or the manganese I should say, is +7. And we'll learn after this lab why. So I'm just going to fill this up. Actually, I'm going to rinse. We know the first thing we do with burettes is we rinse with the titrant first because we don't want it diluted. So I'm just going to rinse that little bit. And once that's rinsed, I'm going to add up to the line. This little beaker here, my friends, has the 10 milliliters of the Fe plus 2 solution, and it's 10 milliliters, and also has 10 milliliters of sulfuric acid to give it the acidic environment that this redox reaction requires. Okay? And once that is done rinsing, I'm going to fill this up to the 50 milliliter mark, and that'll be enough for both of our titrations. Don't forget, the first thing we're doing now is figuring out the actual concentration. We need to standardize this. I'm going to close this up. I just rinsed, and now I'm going to fill this beer up, okay, all the way up.
So pretty.
Yeah, it does. People think things with color always taste nice, okay, and not a good idea. Okay. All right. So our burette is now filled. I'll even zero it out a little bit because I'm just that tall. Okay. So here comes our Fe plus 2. Okay. And someone's going to start titrating. All right. Someone's going to start titrating that. Okay, someone's going to do it. Okay. We'll keep the identities of the people. This is student L, student E. Okay.
There's two student E's.
Yep. And yeah, there's two student. Yeah, we have two E's. Okay.
E-H.
Oh, okay, that's a problem.
So what am I doing?
So now you're going to titrate. We're starting at 0.
Okay, I gotta get how many go down.
You got to figure out how much you go down, and you know when to slow down because the color will start
Wait, what does it
persisting.
start at?
Starting at 0. Okay. If you notice, the color is not persisting. That purple color is going clear, not because it's a chemical indicator, because the Mn plus 7 is grabbing electrons from the oxalic acid and becoming Mn plus 2, which is a colorless color. Due to crystal field theory, we'll understand that. So you'll know when you're getting close when the color starts persisting, and I think it is. So now you want to go drop by drop. You guys are all experienced titrators. You can see that color persisting. So it's cool to, oh, slow down, slow down. Okay. So that's the approximate endpoint. We'll use it, okay? It's not too dark, so now we're gonna measure the final volume. Now, make sure you be reading at the 2 decimal places.
It's like 23.5.
23.5?
Or 22.5, I guess. Yeah.
20, you need 2 decimal places.
0.50.
Okay, if you think it's on the line.
I think it's like exactly.
Okay, so you said 23.50?
Yeah.
20. So you guys got the volume to be 22.50 milliliters, correct? That delivered the exact number of moles of manganate that was needed to oxidize the oxalic acid. So we're going to put the volume here. That's remember it's got to be in liters, 0.0225 liters. Okay, we're good there. Now to solve for the molarity, I take the molarity of my solution, Fe plus 2, times it by my liters. Molarity times liters is moles. I got 0.00 moles. From my balanced chemical reaction, what am I going to do? Well, it's a 1:5 ratio. I'm going to get rid of iron plus 2 to get moles of manganese. So I divide by 5. And when you divide by 5, what do you get? Is that 2 times 10 to the negative 4? I believe so. 0.001 divide by 5 and 2 times 10 to the negative 4, which is 0.0002. That's your moles. That's the moles of your permanganate. You found the moles of Fe. You know that it's a 1:5 ratio because 1 manganese needs 5 electrons. That's how it works. So to find the molarity, now that we have the moles of the permanganate from the stoichiometry, we're going to find the molarity. So 2 times 10 to the negative 4, divide by 0.0225, and I get my molarity of the potassium permanganate to be 0.0089. Does that make sense? It's supposed to be 0.01, but it's a little bit less. Why is it a little bit less? Because potassium permanganate is so gosh darn reactive. That's our known concentration. I'm going to take this away and put 0.0089. Okay? All right. So next titration. All of this got me to the actual concentration. So the next titration is the one where we're actually going to solve for the main purpose of this, is to find the concentration of oxalic acid. So you're turning to the next page now. And so here's what we do know. The titrant now is oxalic acid, H2C2O4. We have 25 milliliters of it. We do not know its concentration. That's the purpose here. Okay? What do we do? What do we know now? After the standardization, we know that the concentration of the potassium permanganate is 0.0089. O'Reilly. Sorry. All right. Now, so what we're going to do now is to do the same kind of math. How do I solve for this? We're going to titrate this. It's going to go clear until it persists. We're going to stop. To solve for the molarity of this, molarity, of course, is equal to moles over liter. Okay, we're going to have this liter is 0.025. It has to be in liters. We're going to need the moles of oxalic acid. As a classic titration, we're going to get that here. So we're going to add some volume. We're going to measure this volume, okay, of KMnO4 needed to what? Reach the end point. And it's when the color persists, we've oxidized all of the oxalic acid this time. So we're going to take that volume in liters, whatever that might be. We're going to times it by its molarity. In this case, it's 0.0089 m. Molarity times liters. Hey, that's going to give me moles of MnO4. And somehow, I got to times it by the ratio of MnO4 to oxalic acid, H2C2O4. I need to know this ratio to get the moles of oxalic acid. So, to do that, I have to do another balancing. So let's go do that together. This is the same stuff that you were doing in the acid-base titrations, except the extra step here is doing the balancing to get the actual ratios. Because in the acid-base stuff, hey, 1H plus was 1 hydroxide. Okay? So we're going to now balance this. Now, I'm going to keep the top one here because I know that the permanganate ion, when I do it, is going to give me 5 electrons. It's the same steps. Balance all things other than O and H. Balance the O, there's 4 of them, 4 waters. That gives me 8 H pluses. To balance the charge so that both sides have the same charge, I put the 5 electrons. Okay, the other piece, the other half reaction, okay, you have oxalic acid, H2C2O4. Now, I'm going to change this. In the worksheet, I have it going to H2CO3, carbonic acid. We're just going to go to CO2 here. I'm going to change it to CO2. Okay, so we got to do this. More advanced balancing here in acidic environment. Hey, balance all things other than oxygens and hydrogens. Well, carbon is 2. There's 1 carbon here. I throw a 2 here. Now I got to balance my oxygens. Well, I think they are balanced because 2 times 2 is 4 oxygens. And I have 4 oxygens here. Here I have 2 H's. Got to balance those with 2 protons. Hey, this side is 0. This side is plus 2. To balance both sides, I have to add electrons. Well, I add 2 electrons. So the -2 and a +2 is 0. This side is 0. Both sides have the same charge. Now, to get the overall balanced reaction so that I can get the overall ratios of these chemicals, I have to balance my electrons. What's a common factor between 2 and 5? 10. So to make the top number 10, I multiply by 2. And that gives me 10 electrons. That gives me 16. 2, 2, 8. To get 10 electrons on the other side, I multiply by 5. I distribute the 5 across. 5. 5 times 2 is 10. 5 times 2 is 10. 5 times 2 is 10. And once you balance your electrons, party people, you have balanced everything. Cancel your little hearts away if you can. Let's write the overall reaction. 10 electrons cancel, so we don't write that. All right. And look at here, there's 10 electrons here, 10 protons and 16 protons. So that goes bye-bye, and this goes to 6 protons. Everything else I don't have to balance. So the overall balanced reaction is 6 protons plus 2 permanganate ions plus 5 oxalic acids gives me 2 manganate, or I should say manganese, plus 10 CO2 plus 8 waters. And that's the overall balanced reaction. And when you balance redox reactions, you should always check to make sure the charge is the same on both sides. Hey, 2 times -1 is -2, plus +6. Okay, that's +4 on this side. And hey, 2 times +2 is +4. These are 0. This side is +4. And the reason I just do that is to make sure that I balance correctly. I'm balancing my mass and my charge. But the whole purpose here, party people, was to get the ratio. What is the ratio between? Here it is. There is 2 of these to 5 of these. It's a 2 to 5 ratio. So when I do my math, there is going to be 5 of these to 2 of these. I'm going to take the moles of KMnO4 that was delivered to completely oxidize the oxalic acid. I convert it to oxalic acid by doing this ratio. I use the volume, and that's how I solve for molarity. Hey, okay, let's go titrate this. All right. Now, so I'm quickly kind of heating this solution up here, oxalic acid with a little bit of heat. In fact, I'll speed things up here with a microwave. All right. She's warm. That's all we really need. Okay, I need my final titrator.
I volunteer not to.
Okay.
I'll go.
I made fun of someone before, so they're all gun shy.
No one wants to go now.
No. Okay. So we're going to go from student L to student E. And now, before you titrate, you better write down your starting value.
22.50.
22.50. Okay, because you're going to have to subtract from that.
So that's the initial volume?
That's your initial volume. Okay, same thing. Start adding carefully your potassium permanganate, which is going to go clear because the +7 goes to the +2. And when it persists, you know that you're getting close.
So when it turns purple?
Yeah, turn it on a little bit. You can open it up a little bit. I'm not going to yell at you yet.
Okay. Yet.
Okay, yes, that's the key word. Now, you know when you're getting close when the color lasts a little longer, right? Okay. And right now it looks like it's dissipating. Again, there's no acid-base indicator here. It's the color change of the oxidizing agent. Once it gets reduced, there's a color change. So if you look carefully, you can see that there's a start of a color change. And it's starting to persist a little bit. Student E is doing a great job. You get a little shout out right there. We're getting close to the end of the burette too. Okay, so like I said, I calculated that 1 burette full of 50 would be enough for both. We'll see if my math makes any sense. Looks like it's persisting. Did we stay purple? I think you're staying. Stop. Let's see her persist for 30 seconds. Nope, so add a little more. A little more.
That was good.
Just a tiny bit. Drop it or something.
There we go.
Is that still color? Is that a color change? Yeah, definitely, yeah.
Should I stop it?
Yeah, I would. Okay, so find that final volume.
I mean, it's like below 50.
So just do an estimate of what you have there.
I mean, I did a couple extra drops by accident.
Okay, so
about 50,
so you want to say you did extra drops after 50?
kind
All right, so 50.00. That sounds like yeah, looks like it may have been just a little bit past the end point.
of. I mean, it's starting to
What
like.
was the total volume of potassium permanganate when you subtracted the two initial and finals? 27.5. So 27.5 milliliters. Okay, that becomes 0.0275 liters. That's the volume of oxidizing agent you added. This is the molarity that we standardized. I'm going to multiply molarity times liter to get my moles. That's just a classic AP Chem, thing that we do. 7.5 times by 0.0089. And so what I get is 2.44. 2.44, let's carry another extra significant figure, 8 times 10 to the negative 4, and that's moles of MnO4 negative. So what am I going to do with that? I need moles of my oxalic acid. The whole point of the lab is the molarity. What is the molarity of this? I know the volume, I need its moles. Well, using the balanced redox reaction, if I got the moles of this, it's a 2 to 5 ratio. So I'm going to get rid of potassium permanganate. That's why the manganate ion's on the bottom. So I'm going to times that value of moles that I just got. I don't know, I should have gotten 2.44. Looks like I cleared my calculator. Oh, there it is. Take that, times it by 5. Divide it by 2. And now, party people, I've got 6.119. 6.119 times 10 to the negative 4 moles of oxalic acid. That's the whole point of, I'm using the mole ratio. Classic stoichiometry. And I'm going to divide that by 0.025 because I know that I started with an analyte of 25 milliliters. And when I do that, I get a molarity to be 0.0245 molar. That's the molarity. Equal to the concentration of my oxalic acid. That's the molarity. Probably carrying two significant figures, so 0.025, 24, sorry. What was my number? 245, 244, so 0.024. I made 0.025.
Wouldn't it be 0.025? Because it's round up.
It was 0.02447.
Oh.
So the other number, okay? So I made 0.025. We're getting 0.024. Not bad. I made that oxalic acid last year, so it could be degrading. Good number. Okay? Good number there. All right? So there's your lab. That's it. There's nothing to it. Okay? But the key to it is that we did a volumetric titration using not acid base, using strong oxidizing agent, drove the reaction, and we used the color change of the oxidizing agent when it grabbed electrons to tell us when to stop the titration. There was no pH probe, there was no change in pH, there was no acid-base indicator. And we didn't use a 1-to-1 ratio, we had to actually find those ratios by balancing and then using those ratios. Okay? So great little lab there.